Hey there, this is our module overview and brief lecture video for multivariate analysis of variance. As with all the modules, start with the README file that lists the readings for the week, as well as links to the data analysis and quiz assignment. We're going to start off with the Tabachnik and Fidel chapter on multivariate analysis of variance and covariance. Also read through the notes I've made, try to summarize some of the readings on multivariate analysis of variance. We're going to walk through those. And then I have 3 journal articles. One that gives you sort of a primer on MANOVA, and he specifically focuses on the discriminant analysis follow-up, which we're not going to cover, but you can read about it here. And this next one is sort of a critique of MANOVA and various alternative statistical tests you might want to consider as well. And then the next is an oldie, but it's a good article on kind of the difference between multivariate analysis of variance versus multiple univariate analysis of variance test. So you can see those there. You can also download a zip file with all of the readings in them if you want. And we'll go through my notes on analysis of variance in a minute, kind of hit the high points. I've made a YouTube video of just me walking through analysis of a multivariate analysis of variance. You can see that there. Here's the example that I'll walk through: the SPSS data set, a sample syntax file, and then a results write-up. So you can see the example gives stats for conducting the test in SPSS, a research scenario, some data, and then annotated output. Also, walk through this in the other video for you as well. You can see I also did a write-up of those results here, so you can see how you would write up these results and sort of present them. So let's talk a few minutes about multivariate analysis of variance. MANOVA, what happened? I need this. There we go. MANOVA is basically just an extension of analysis of variance, but for instances where we have more than one dependent variable. So, in ANOVA, we have one dependent variable, and we're looking for group differences on that dependent variable. In multivariate analysis of variance, we have more than one dependent variable, and we're looking for group differences on that combination of dependent variables. It's used for a case when our dependent variables are correlated, and we want to take that relationship among the dependent variables into account. Here's an example research scenario. A researcher is interested in the effect of a type of test on whether the students took the test using a paper and pencil test or online, like a digital test on the computer. So, we have students enrolled in both a biology and statistics class. Half the students, so 50% of the students, 50 students in the stat class took the final exam on paper and pencil. 50 students took it on the computer, and the same thing in their biology class. The same 50 took it paper and pencil in the stat class, took it in paper and pencil in the biology class, and same thing for the students in who took it on the computer. So you can see we have two dependent variables. It'd be student scores on their final, scores on their stats exam final and scores on their biology exam final. And we have one independent variable in this case, the type of test they took, whether it was paper or digital. And so we'd be testing basically the null hypothesis that there is no effect of the type of test across the different exams against the alternative hypothesis that there is a difference in the type of test, whether it was paper or digital, on students' final exam grade. This would what we might call like a one-way MANOVA, similar to what we had like a one-way analysis of variance. Is when we have one independent variable. You might also hear it called like a two-group MANOVA because there's only two groups in the independent variable. I'm only going to discuss the one-way ANOVA. Both of the examples, but the example that I give on Canvas and the homework are both two-group one-way MANOVAs. But all the concepts extend to the same thing, to like factorial MANOVA. Same thing we had factorial ANOVA where we have two or more independent variables. You look for an interaction between them. We're going to just keep it easy for this first introduction. So some of the assumptions, here we go, the assumptions in MANOVA are similar to the ones we make in analysis of variance, but we sort of just extend it to the multivariate case. So we have basically the same assumption of independence. Basically the observations within each sample are independent. So in our example above, scores on people in the paper group in no way impact the people in the digital who are taking the test using the digital means, is what we mean by independence. So we have another assumption of normality, but in this case, it's referred to as multivariate normality. And multivariate normality is a little more stringent assumption than just univariate normality. So having univariate normality within each one of your groups on each of your dependent variables is a necessary but not a sufficient condition for multivariate normality. So if you don't have univariate normality, you don't have multivariate normality. But if you have univariate normality, that doesn't guarantee that you have multivariate normality. However, the best way to basically check for multivariate normality is really just to accept is to examine basically the bivariate univariate normality. There are a few formal tests for multivariate normality. None of them are currently available in SPSS. The assumption of homogeneity of variance sort of extends into the multivariate sense with this homogeneity of variance, covariance matrices. We assume that the variances and covariances among within each one of our dependent variables are the variances and covariances across our dependent variables within our independent variables are equal across dependent variables. We'll have a boxes M test. We'll test for violations of this. Usually typically if we have equal sample sizes or approximately equal sample sizes within each group, the general rule of thumb is like as long as the largest group sample is at 1.5 times the size of the smallest group sample, then you're probably okay here. Violations assumptions probably aren't too serious. But equal sample sizes helps protect against violations of this assumption. If you're going to do a multivariate analysis of covariance, Or if you're going to perform the step-down analysis post hoc, you also want to include all of the different same assumptions that we had in analysis of covariance. Basically, that the covariates are linearly related to the dependent variables, the homogeneity of regression, so the impact of the covariate on the outcome is the same for each level of our independent variable, and you want to make sure that your covariates are reliable as well too. Other important data considerations, unequal sample size, drastically unequal sample sizes, and violating this assumption of variance covariance matrices can make the estimation unstable, and you might not. It might be impossible to analyze the data. Or you might get some funky results. So, equal sample sizes is typically helpful in multivariate analysis of variance. Your choice of dependent variables is also something important to consider. MANOVA tends to work best with highly negatively correlated dependent variables, and it typically works pretty good when the dependent variables are, say, moderately correlated, maybe around 0.5, 0.6. It doesn't work too well when your dependent variables are really highly correlated. So if your dependent variables are highly correlated, like at 0.9 or really close to 0, MANOVA doesn't work as good. The idea is that, if your dependent variables are really highly correlated and they're probably measuring the same construct, so it might just be redundant information. If your dependent variables aren't correlated at all, basically the correlation is near 0, you're really not gaining much then by moving to a MANOVA. Separate univariate ANOVAs with a Bonferroni adjustment might be just okay. So it's important to kind of consider these things. It's not to say that you can't have highly correlated variables. You just might want to watch out that you're not measuring the same construct with both outcomes. So there are 4 different criteria for assessing whether the multivariate test is statistically significant. One of them is called Wilks lambda. Wilks lambda is pretty much the one we probably usually default to. It's typically the multivariate statistic you'll see reported most of the time. And so if, we tend to meet all the assumptions, everything else, looks pretty good, we'll usually report Wilks lambda. Hotelling's trace is usually recommended when your dependent variables are uncorrelated or aren't strongly correlated. It also has a special meaning when you only have 2 groups on your independent variable. Basically the independent samples t-test can be like generalized to a multivariate sense, and then you might hear it called like Hotelling's t-squared statistic instead of MANOVA. But when your independent variable only has 2 levels, all 4 of these tests will be congruent. So it doesn't matter really which one you report. And I usually default to just Wilks lambda. Again, in that case, Play's trace here is usually reported when you violated some assumptions. So if we're not exactly sure about the multivariate normality, or our homogeneity of variance is maybe questionable, we might want to report this statistics. Roy's largest root here is usually best with highly correlated dependent variables and tends to be the most conservative criterion. Again, when all of your independent variables have just two levels, like in the example we had above with the two different types of tests, whether they were paper or digital, all four of these are going to be the exact same. The values of each one of these, of the values of lambda, the values of trace, the value of the largest root are all going to be, or might be slightly different, but the F-test for them and the associated p-value will all be the same. So if you have a statistically significant multivariate effect, right? So it's saying that you know, that your two groups differ on some combination of your outcome variables. The next thing you'll want to do is a follow-up test, and there are generally three follow-up tests you can use to assess your individual dependent variables. The most popular and the easiest to do is just to do univariate analysis of variance test. This is probably the most controversial one. If you are going to do this, and SPSS does this for you by default, is you'll want to make a Bonferroni adjustment for the number of tests you're going to perform. So if you had 4 dependent variables, you would take your alpha level, say 0.05, and divide it by 4. And you would use that to compare the p-values to all those univariate F-tests. If your dependent variables are highly correlated, then this follow-up test could lead to an inflated type 1 error rate. When your dependent variables are highly correlated, and you can sort of rank them in sort of an order of priority, like this dependent variable is my highest priority, followed by the next, especially if you have like some type of theoretical argument for why one might be more important than the other. Then you can use what's called this was called a step-down analysis. Basically, in the step-down analysis, you assess your highest priority dependent variable just using a univariate ANOVA. Then you assess your second highest priority dependent variable using an analysis of covariance with your highest priority dependent variable as a covariate, and then you continue on with that. So your third highest priority variable would then be tested with an analysis of covariance with the first two as covariates. And you can get SPSS to perform this analysis for you, but they'll only do it through syntax. And I've provided you that syntax on Canvas as well. The other follow-up, and one that's generally one of our articles we're going to read, the author of that article argues that the descriptive discriminant analysis should be your main follow-up. And the basic argument is because it keeps it within the multivariate framework. However, you'll see really discriminant function analysis sort of beyond the scope of this class. You can read about it a little bit more in that article. Most of the time you'll see univariate ANOVAs probably 75% of the time, step-down analysis, another 10, 20% discriminant analysis, followed another 10, 20% as well. If you have a factorial MANOVA, and you have a significant interaction effect, you got to perform simple main effects analysis. Same thing, if your independent variable has more than 2 levels, you need to do some type of post hoc test on yours. Oh, that should say Tukey, not Rookie, and should be. You can see, so, different effect sizes for MANOVA, you know, just like analysis of covariance, you can get an eta squared statistic. It's typically calculated as 1 minus Wilks lambda. In the two-group case, the eta squared and partial eta squared that SPSS computes are congruent in that case. In the when your independent has more than 3 levels, they'll be separated some. But SPSS will provide the partial eta squared value for you, and you can report that as well. In the example, I talk about another effect size, another multivariate effect size that's applicable, the Mahalanobis distance, that you can calculate when you just when your independent variable only has 2 levels, but it's only applicable in that case. It's basically an extension of Cohen's D to the multivariate sense. And then, you know, kind of what to include here in a MANOVA write-up. You know, I want to mention the test you're doing, whether you met the assumptions underlying it test. What criteria did you use to assess the statistical significance of the MANOVA? I couldn't get that out. You know, did you use Wilks lambda, Roy's largest root? Just let your reader know. You know, report the results of the test and report an effect size like partial eta squared. And then mention what kind of follow-up test you did. You know, did you do univariate ANOVAs with the Bonferroni adjustment? Did you do a descriptive discriminant analysis? Did you do a step-down analysis? And give the results of that follow-up as well. Here's an example write-up that I found in the literature. There's also an example write-up from Tabachnik and Fidel, and I've also provided you a write-up on Canvas as well for our example. So that was our quick module overview and brief lecture. If you have any questions, concerns, please shoot me an email or post in the message board. Thank you.